this episode of Remote Linear Algebra, we will be looking a little more deeply at the characteristic polynomials that go along with eigenvalues. So we have an example polynomial here, and if we knew that this polynomial came from a matrix that was diagonalizable, I would be able to just use the graph to come up with the eigenvalues and the diagonal matrix that went with the matrix A. So notice -7 is one of the zeros, and look at the shape of the graph. It looks like a cubic polynomial. So -7 must have a multiplicity of 3. That is, the factor x plus 7 shows up in the polynomial 3 times. So here's one of the zeros, -7, and it has multiplicity 3. Another zero is 1/2 right here. And notice the graph just slices through, kind of straight through. So 1/2 has multiplicity only 1. The graph slices through like a line, and so it has multiplicity just 1. And then there's a third zero that looks like it's 3. And notice that the graph right around 3 looks like a little parabola. So 3 has multiplicity 2, meaning x minus 3 shows up in the polynomial 2 times. So x minus 3 times x minus 3 will be in the polynomial. So the zeros of this graph are the eigenvalues, and if we know that the matrix that had this as its characteristic polynomial, if we know that it is diagonalizable, then we can just use those eigenvalues, or the zeros, to build the diagonal matrix. And this would be its diagonal matrix. 3 would show up twice, -7 would show up 3 times, and 1/2 would show up once. And then remember, all of the other values are zeros. Another example here. Here I've got another polynomial. If we made the assumption that this polynomial was the characteristic equation of some matrix, and we knew that that matrix happened to be diagonalizable, remember, not all matrices are diagonalizable, but if they are, then the characteristic equation zeros tell me the eigenvalues, and that tells me what the diagonal matrix is. So notice 0 is a zero of this polynomial, and the graph just slices through like a line. So that means that 0 has multiplicity 1. And then another 0 looks like it's 5. And look at how flat that curve is. But notice I hit the graph and I turn back around. In fact, it almost looks like a whole bunch of numbers kind of in line around 5 or zeros. But that's just because the calculator can only draw it so fine-tuned. Because it's so flat, but it's rounded like a parabola, it's an even power. So we're going to say that it's 4, okay? Because we need to make an answer. But it's not squared, because squared would be much like a sharper turn. The higher the power, the flatter it is. So it's probably a 4th power. So we're going to say it has multiplicity 4. So that means that x minus 5 shows up in the polynomial 4 times. So my 2 eigenvalues are 0 and 5. And if it came from a diagonalizable matrix, then the diagonal matrix would have 5 in the diagonal 4 times, and then 0 showing up once. Remember, the order that you put the eigenvalues in the diagonal matrix doesn't matter, but once you put those, then how you define the matrix P that works with that diagonal matrix matters. So when you're defining P, eigenbasis vectors involving 5 have to show up in the first 4 columns, and then the eigenbasis vector that would go with 0 would show in the last column. And same thing here, when I found matrix P, I would have to put the basis vectors for 3 first, then the basis vectors for -7, then the basis vectors for a half. By the way, we also know that for this example, A would be not invertible. That is, A inverse would not exist because 0 was one of our eigenvalues. If 0 is an eigenvalue, then you know A is not invertible. Some other questions related to this topic. Again, suppose you have a graph that you know comes from a diagonalizable matrix, and looking at the zeros, we see that -4 is a 0, 6 is a 0, 9 is a 0, and 12 is a 0. So -4, 6, 9, and 12. Now the graph just slices through at -4, 9, and 12. So each of those have multiplicity 1. But around 6, it bounces on the x-axis, and right in that neighborhood, it looks like a little mini parabola. So 6 has multiplicity 2. So because we know it came from a diagonalizable matrix, then -4 has an eigenspace of dimension 1, 6 has an eigenspace of dimension 2, 9 has an eigenspace of dimension 1, and 12 has an eigenspace of dimension 1. And then we're asked whether we or not we know if A is invertible. We know A is invertible, that is, A inverse exists, because 0 is not one of my eigenvalues. If 0 is an eigenvalue, A is not invertible. If 0 is not an eigenvalue, A is invertible. And that's because if 0 was an eigenvalue, it would mean that A times X would equal 0, and it would have only the trivial solution. It would not have the trivial solution if 0 was an eigenvector or eigenvalue. But 0 is not an eigenvalue, so A times X equals 0 has only the trivial solution. And then they want us to build our diagonal matrix, so here it is. -4 shows up once, 6 shows up twice, 9 once, 12 once. Again, the order doesn't matter, but once you get the order, it has to have the basis vectors in P line up. So then we're asked, well, how would we come up with P? We're not actually given A, and we're not given enough information to find A from just the polynomial. All we know is that it's diagonalizable, and we do know what its diagonal matrix is. But in order to actually get A, I would have to be able to build P, or have some other workaround. But if we were going to build P, what we would do is you would find the row reduced form of the original A minus -4 times I, and when you row reduce that, it would give you the basis vector for -4. You would do the same for 6, and it would give you a basis vector for 6, but because we know it's diagonalizable, there would be 2 of them. And then we would do the same for 9, and we would get the basis vector for 9, and then we would do the same for 12, we would get the basis vector for 12, and then once we had those basis vectors, P would have those basis vectors as the columns. -4's basis would go first, then the 2 that we obtained for 6, then for 9, then for 12. Again, they're in this order because that's the order that I put them in the diagonal matrix. Looking at a last example here, determine the basis for the eigenvectors of the following matrix, and then state each basis along with its associated eigenvalue. Well, first of all, notice that my matrix is triangular. Triangular means that zeros form one triangle of the matrix. Actually, diagonal matrices are kind of a special version of triangular matrices, but usually if the zeros are on both sides, we just call it a diagonal matrix. So this is a triangular matrix. If you have a triangular matrix, then the eigenvalues are the diagonal values. So you don't have to do any finding of a characteristic equation. All you have to do is look down the diagonal. -2 is an eigenvalue, 4, and then 5 shows up twice. So if we did have the polynomial for this particular matrix, 5 would have a multiplicity of 2, 4 would have a multiplicity of 1, -2 would have a multiplicity of 1. If I RREF for -2, this is the matrix that I'm row reducing. Notice that I took -2 minus -2, gave me a 0. 4 minus -2 gave me a 6. 5 minus -2 gave me a 7. 5 minus -2 gave me a 7. And then all of the other values stay the same. So the diagonal is what gets changed to find your basis vectors. So if you find the row reduced of this particular matrix and you read it off, you get a form. So any multiple of this form would be fine. I chose the fraction form. So x would be -49/15, y +49/15, z -28/15, and then 1 for w. I could have picked 15 for w, and then these would have been the numerators. So any matrix that's a multiple of this can be used as a basis vector. Doing the same for 4. So the matrix that we're going to row reduce, -2 minus 4 is -6. 4 minus 4 is 0. 5 minus 4 is 1. 5 minus 4 is 1. And then all the other values stay untouched. If you row reduce that, then you get a matrix that gives you this as the basis vector. So x ends up having to be 0, and then y and z are related to w in terms of y would be 1/3, z would be -1/3 if w was 1. So once again, any vector that's a multiple of this vector would work as a basis vector for 4. And then for 5, the vector, or the matrix that gets row reduced is this one. The -7 is because we take -2 minus 5, and then 4 minus 5 gave me -1. 5 minus 5 is 0. 5 minus 5 is 0. All of the other values stay the same, and that actually simplified down to a basis vector of 0, 0, 0, 1. X, Y, and Z all have to be 0 to satisfy the information you get in the RREF, and then W can be 1. Notice that we have a 4 by 4 matrix, and we had technically 4 eigenvalues if you consider the multiplicity of 5, but when it came down to it, 5's basis only has one vector in it. So we only have 1, 2, 3 independent basis vectors. So it turns out that this triangular matrix is not diagonalizable. So up here we were assuming a diagonalizable matrix. Here we were actually given a matrix A and we were investigating it, but it turns out it is not diagonalizable because A is 4 by 4, but I only have 3 independent basis vectors. There would need to be 4.